Okay, so let's talk about parametric equations for a second. Suppose you're given x and y as functions of a third variable called t. So we're going to call t the parameter, and instead of having y equals f of x like usually we would have, such as y equals x squared or something like that, we're going to have that y itself is a function of t, like you have at this example, in this example at the bottom, and x is also a function of t. So x is something that depends on t, and y is something that depends on t, and t is just free. Whenever this happens, we're going to say that these are parametric equations. So we can't say it's one parametric equation, right? It's a set, a pair of parametric equations. There are two equal signs. And for each value of t, this is going to generate a different point x and y that we're going to find by plugging that value of t into the set of parametric equations. And that point can be plotted into the xy plane. And as t varies, those points put together are going to trace out a curve that we call a parametric curve. Okay? T doesn't usually represent time, but I will act most of the time as if it does, because that's the most common usage of parametric equations here. Generally, I'm going to pretend and use t as time and x and y as positions in the xy plane. And understanding or keeping this intuition in mind also helps understand what's going on most of the time. So as an example, let's trace out this curve that's given by these equations: x equals t squared minus 2t, y equals t plus 1. The most basic way to do that is to have a table of values. And let's say I start my table of values with t values. Let's say -2, -1, 0, 1, 2, maybe. And again, you can think of this as, okay, where is my point xy when t equals -2 seconds? And then where is it when t equals -1 seconds? And then where is it when t equals 0 seconds, when t equals 1 second, when t equals 2 seconds, and so on. Right? And so I'm going to calculate the x values for these t values. So the t values are going to give me the x values. So let me extend this table a little further, and let me actually just plug in t. So when I plug in t equals -2 here, I'm going to get -2 squared plus, or -2 times -2. So that will be 4 plus 4, which will be 8. Okay. And then when I plug in -1, if I go a little faster, this will be +1 plus 2, which will be 3. So there's the 8, there's the 3. 8, 3. And then when I plug in 0, x is going to be 0 because it's going to be 0 squared minus 2 times 0. When I plug in 1, this will be 1 minus 2, which will be -1. When I plug in 2, this will be 4 minus 2, which will be 2. And then I can do the same with the y values. And so let me extend this even more so I can fit the y's into my table. You don't have to keep your calculations as detailed here like I am doing with my table. You can have a separate sheet where you do the calculations yourself, or you can do that in your head most of the time. Mental math is fine at this level. And so for y, the math is a little easier though. And for y, we're going to have -2. When t equals -2, we're going to have y equals -2 plus 1, which is -1. And then -1, when t is -1, y is -1 plus 1, which is going to be 0. And then 0 plus 1 is going to give me 1. And then 1 plus 1 gives me 2. 2 plus 1 gives me 3. Okay. So y is just going to progress one step ahead of t. And one last column in my table here is going to be, just because I want to, you don't have to do this yourself every time. Just want to make it very clear what is the xy pair itself. It's 8, -1, and then 3, 0, and then 0, 1, and then negative 1 comma 2, and then 2 comma 3. How does that help me plot my curve, trace out my curve? Obviously, just plot these points in the xy plane with one extra caveat they have to keep in mind. So I'm going to go ahead and draw an xy plane somewhere here below, but I also want to keep, let me see if this is the right decision. My x's are going to vary from 2 to 8, from negative 1 to 8 actually. So I don't need a lot of space on the left. And my y's are going to vary from negative 1 to 3. Okay, so I think this is fine. Extend this a little bit further to the right. Then I expand it up or down. This is going to be my x and my y. And again, y is going to vary from negative 1 to 3. So I'm going to do a negative 1 right here. This is a 1. This is a 2. This is going to be a 3. And I can follow units here. Do I have enough space on the right? Let's see. 2, 3, 4, 5, 6, 7. Maybe I can expand this a little further to the right. So maybe we just a little more is fine. And so let me go ahead and actually label these. I'm just trying to be careful. Don't really have to do this. I'm just trying to be careful. And then let's plot the points. First is the point x equals 8, y equals negative 1. That's right here. And then x equals 3, y equals 0 is right here. X equals 0, y equals 1 is right here. X equals negative 1, y equals 2. It's supposed to be right here. X equals 2, y equals 3. So you see we're going the other way now. Should be right here. Let me double check this to see if everything's okay. Go back. When t is 2, that's 4 minus, yeah, see, I could tell that this was wrong. There was a mistake right here. So let me do that in red. This is going to be 2 squared minus 2 times 2. So that's 4 minus 4. That's actually 0. So that is the correct y coordinates here. It's going to be a 0 for us. So I have the point 0, 3 instead of the one that I originally plotted. Okay. And of course, we're not going to plug in all values of t, let's say between 0 and 1, or between negative 1, like 0.1, 0.2, 0.3. We're not going to plot these. But generally, it's safe to assume that if you did, these will be connected by a smooth curve. Everything here is smooth. The curve is defined by these nice polynomials in t that you see above here, nice polynomials that you can use. And so it's fair to assume that the curve is going to trace out this sideways parabola. But maybe this is not exactly going to be a parabola. It's just going to be something that resembles a parabola. But there's a way to make sure. I'll show you that too. So here is also another thing that we can tell. If we assume that t is time, we also know the direction that the curve, that the points on the curve are moving. So that was the first point because it was the earliest time that we had. And the second point that I got was this point. Of course, there are a bunch of points in between, but I do know that the curve is moving in this direction, right to left in this piece. So this is something that you didn't have before for regular Cartesian equations. Another thing, as I've said, that we can do is making sure, let me actually work on this a little bit on the side here. If I go back and I look at this pair of equations, Here's one thing that I can do. I can look at this equation and see that if I move this 1 over to the left side, I'll get that t is y minus 1, right? And now that I know that t is this, I can take this t value and plug that back into x, yes? And that will give me that x is y minus 1 squared minus 2 times y minus 1, which I can expand. And I'm going to zoom in here just so we can have a good look at what's going to happen. This is going to become, as I FOIL this, y squared minus 2y plus 1 minus 2y plus 2, x equals y squared minus 4y plus 3. And this is now a new equation where x is a function of y. There's no more t involved. So this is, again, we call this a Cartesian equation. In contrast to the parametric equations, excuse me. And of course, looking at this, if you remember previous classes, you can tell this is a parabola. If x and y had swapped places, then you could tell this was a parabola, ax squared plus bx plus c. But now it's x and y have swapped places. So this is a sideways parabola like we have here. And so we know exactly what's going on. Okay. And this process that we just did is what's called eliminating the parameter. So t is the parameter, and we were able to, through this process, get rid of t and just have a regular Cartesian equation for x and y. And the graph coincides with the graph that the parametric equation, the set of parametric equations represents. But then we lose a little bit of information, like I said, because the time variable, the parameter, tells us where the particle is at a given time, and so we can figure out the direction. Where is it going at each particular instance? And so this is a little bit more difficult to trace in parametric equations, but also it carries more information. Another thing that we can look at here is whenever you're given something like this, you can immediately try and eliminate the parameter instead of trying to find t values. It's not a big deal. For this one, you could definitely build a table yourself. I'll let you do that, but you can look at t values that are nice t values to plug in. Of course, I'm not going to do t equals 1, 2, 3 because those are difficult values to plug into x and y there. What's the cosine of 1? What's the cosine of 2? Those are difficult things for me to do without a calculator. But I could definitely look at the notable angles such as pi over 6, right? Then pi over 4, then pi over 3. I could do that. Place them on all of those points on the xy plane and figure things out. But I can also, I'll let you do that yourself. It's a good exercise, I think. But eliminating the parameter also helps, and helps very quickly. And the tell here is to remember that you already know that x squared plus, that cosine squared plus sine squared equals 1. You already know this. This is the fundamental relation of trigonometry. And because x is the cosine and y is the sine, this is just saying that, if I just take one extra step here to make this very, very obvious, x squared plus y squared equals 1. So we already know what this equation represents. This is a circle of radius 1 and center at the origin. So eliminating the parameter is very helpful when possible for us to figure out what the curve actually traces. Though, like I said, we lose the direction. But if you do also trace the points, you can clearly and very easily if you wanted to tell that this is no longer, or I should say not only a unit circle, a circle centered at the origin, but also a circle that is traversed in a specific orientation. So here's my circle. It's not quite unitary, but that's fine. And if you, for example, just plot in a few points, let's say you have a t equals 0. The cosine of 0 is 1. Your point is going to be 1 comma 0. If you do t equals, so that will be this point right here. And if you say t equals pi over 2, which is 90 degrees, the cosine of 90 degrees is going to be 0. The sine is going to be 1. So this is the next point, which means the curve is being traversed that way. And if you continue, you can tell that the curve is a circle that's being traversed counterclockwise, which is pretty cool, if you ask me. You can definitely find a clockwise orientation or parametrization for this circle. I'll let you try that yourself as well. But the last thing I want to say is that sometimes, right, you're going to be given curves with specific t values. So if I had said, so if you go back, right, if you go back, my curve here, the parameter is free. There's no limitation on what t is allowed to be. And so it's going to continue on forever in either directions, in either direction, because it's just a parabola. Here, my circle, I did give myself limitations from 0 to 2 pi, and so my circle is going to be starting at this point. It's going to end at this point also, because when you plug in t equals to 2 pi, then you're going to get also 1, 0, because the cosine and sine of 2 pi are the same as the cosine and sine of 0. But if I had limited my circle, and maybe I can move this a little bit further down. So if instead I had said that t is between, let's say, 0 and pi over 2, then this curve would only be a quarter of a circle. Because that will be the last t value that I'd be allowed to plug in. And so we'd only have this piece of the circle right here instead of the entire circle like we did before. So this is another advantage of using parametric equations, because they also let us pick only a piece of the curve. And so just to work on nomenclature here, whenever this happens, the initial point that I get by plugging in the first t value is again called the initial point. And the last point that I get is called the terminal point. This is important nomenclature most of the time. Now, another, I guess a couple of pieces of information that are helpful is that whenever initial and terminal points are the same, we give the curve a name. We say that the curve is closed. For obvious reasons. Just contrast what we said about the circle and the quarter of the circle. Of course, it doesn't close. This closed curve has this interior area and this exterior area. So this is why this is called a closed curve. This is not always the case. We can have sort of H-shaped curves here that have the interior divided into multiple parts, but this is still a closed curve because it will start and end at the same time, as long as we don't have any over tracing here.